Alright, so this video is going to be on how to find domain algebraically, so meaning completely by hand, you're not using a calculator at all. So first we're going to write out definitions for domain and range, and I'm going to type them because that's easier with a stylus, but you are welcome to handwrite them obviously, and go ahead and just pause the video so that you can have time to write them down. So the domain is the set of all possible x values which will work in the function and will output real y values. So the set of all possible x values which will work in the function and will output real y values. Typically we're going to find this by hand. Alright, so domain. The range is the set of all possible y values of a function that will result when we substitute all of the possible x values into the function. So the domain are the x values that you're allowed to plug in. The range is the y values you get when you plug those x values in. Okay? And for this, typically, whoa, butchered, nope, no autocorrect. Typically, we will find this using a calculator. Okay, now I'm going to write slow like the rest of you. So those are the two definitions that we want to have. Now within those two definitions, finding the domain algebraically, there are three functions that are important for us to look at. And this is because these three functions have limited domains. And we've learned about them before, these are not new. So the first function that we have learned about is rational functions. And the parent graph of a rational function is y equals 1 over x. Sorry, my hand got in the way. Y equals 1 over x. And if you guys recall, you cannot plug 0 into the denominator of a fraction. No 0 on the bottom. And so that means that here, our domain would be we can have every single x value we want as long as we don't pick 0. All real numbers, x cannot equal 0, right? That would be considered the set notation. It's very, very, very important you have that all real numbers because the domain says the set of the possible x values. It doesn't say just tell me what to exclude. It says tell me what x values I can have. So when I say all real numbers, I'm saying you can have all of them, and then I'm specifying except for 0. So you have to have both of those pieces if you choose to write it that way. If you're going to write it in the interval notation, you would say negative infinity to 0 and 0 to infinity. So you're just skipping 0. Okay, the second type of function that we have a limited domain for is a radical function. And we are going to specify that these are even radical functions, so square root, 4th root, 6th root, 8th root. The odd radical functions do not have a limited domain. So here this would be like y equals the square root of x, or you could say y equals the 4th root of x, 6th root, etc. And here we just remember that when you're taking a square root, you are not able to square root negative numbers, but you are able to square root 0. So here we're going to specify that our domain is any x value that is greater than or equal to 0. I can take the square root of 0, and I can take the square root of positive numbers. If I write that in the interval notation, I'm going to say from 0 to infinity, and I'm using a bracket on 0 because I can include 0. All right, and then one last type of function we have that has a limited domain that a lot of people don't really think about is a logarithmic function. So again, a couple examples of that, we could have y equals log of x or y equals ln x. Those are two very common parent functions for log functions. And here, you might not remember this, but you cannot take the log of 0, and you cannot take the log of a negative number. So here, we're going to say that the domain, sorry, I'm having stylus issues. Whatever you take the log of has to be greater than 0. Can't take the log of 0, can't take the log of a negative. And then in the other notation, not a bracket, parentheses, 0, infinity. So when we look at the domain algebraically, we're going to have potentially one of these situations happening or maybe even a combination happening, and the domain is always going to be the most limited x values we can have. All right, so I'm going to write a note to myself. The domain is, well, I'm going to write always go with the most limited domain. Should have typed that. Would have looked better. Okay. So if you think about it, if you had some people over for dinner and one person was gluten-free and another person was vegan and the third person literally ate anything, then you would probably make a meal that was gluten-free and vegan, so it would be okay for everyone to eat. And that's kind of how we treat this domain sort of issue. If you find a number that's limited in one piece and a different number that's limited in another piece, then the overall domain is going to exclude both of those. So that's what we're going to keep in mind. Okay, so now we're going to go ahead and do some examples that are going to make us think a little bit more. Actually, for all, actually I'm going to write it this way. Sorry. For all of these examples, the instructions are to find the domain. Okay, and we're going to do 4 examples. So this is the first one. First, we're going to work with a rational function, x plus 3. It's being divided by x squared minus 5x plus 6. That's a squared. Okay, so here we recall that in a rational function, the denominator cannot equal 0. So for me to figure out what is going to make this denominator equal 0, I'm going to go ahead and write this equation to solve. So it's not supposed to equal 0, so I am setting it equal to 0 so I can find out exactly what I am not allowed to have. So to solve this, it's a quadratic. I need to factor it. I'm going to look for 2 numbers that multiply to 6 but add to -5. So those 2 numbers would be -3 and -2. So I have x minus 3, x minus 2 as my factors. That means that my solutions are x equals 3 and x equals 2. So those 2 solutions are what would make the denominator equal 0. That means that for my domain, I'm going to say I can have all real numbers, but I cannot have 2, and I cannot have 3. So remember, we're specifying, we're putting that all real numbers there. We're not skipping it, we're writing it there. Another way to write this problem in set notation is you can say that the x values can be less than 2, or the x values can be between 2 and 3, or the x values can be greater than 3. So those 2 notations I wrote, those are both considered to be set notation. Both of those are valid ways to write it. Probably the most common way that you're going to see it written is in that interval notation. So that's where we say negative infinity up to 2. But I'm going to skip the 2 and then do from 2 to 3, but skip 3 and then 3 to infinity. That would be the most common way to see this written. Okay, let's go ahead and do another example. This is going to be example number 2. And here we're going to do f of x equals the square root of x plus 3. So here we have a radical expression. We know that underneath a radical has to be a positive number, or 0. Underneath the radical can equal 0, it can also equal a positive number. So what we're going to do is we're going to take this whole thing that's underneath the radical, and we're going to say that can be greater than or equal to 0. As long as it's not negative, we're okay. So I'm going to say x plus 3 is greater than or equal to 0. And then I just need to solve that. So I'll subtract the 3 over, and I get x is greater than or equal to negative 3, and I'm done. That's it. These radical ones are pretty easy. So I can write in set notation x is greater than or equal to negative 3, or in the interval notation I can say bracket negative 3 to infinity. All right, for our third example, we're going to start looking at functions that have more than one piece to them now, that have more than one term. So this function is going to be 5 of log base 3, sorry, not 5 of, 5 times log base 3 of 2x plus 1. Guys, I swear I'm drawing the top of my numbers. Okay, plus 1 over x minus 7. Okay, so for the first term, we're looking at an expression that's a logarithm, and so we know that we cannot take the log of a negative number, and we cannot take the log of 0. So that means that that part that I just circled has to be greater than 0. It can't equal 0, it can't be negative. So I'm going to write 2x plus 1 is greater than 0. And I'm going to go ahead and solve that. So I can minus the 1 over, and I get 2x is greater than negative 1. And then I can divide the 2 over, and I get x is greater than negative 1/2. Okay, so that's one limitation I have. Now I have to look at the other limitation I have, and that comes from this rational expression. I know that I cannot have 0 in the denominator. So I have to think about what would make that denominator equal 0. So the denominator equals 0, add 7 over. If x equaled 7, that would make the denominator equal 0, and that's not acceptable. So x cannot equal 7. So here, I'm going to go ahead and write my domain. I have two things going on. I have to be greater than negative 1/2, but I cannot equal 7. So I'm going to say that my x is between negative 1/2 and 7, that numbers between those are okay, or x can be greater than 7. That's one way to write it. The other way to write it is to say that I can have from negative 1/2 to 7, but I have to skip 7, and then 7 to infinity. All right, and one last example. We're going to add lots of things to this one. So this one's x plus 2 over x square root x plus 1 plus 3 over x minus 5. Okay. So we have two rational expressions. That means that we have different ways that the denominator could equal 0. So I know that this x right here cannot equal 0 because then you'd have a coefficient of 0 for that radical, and it would make the whole denominator 0. So I'm going to say that my number that I need to not include is 0. My excluded number, there we go. My excluded number for that one is 0. Sorry, brain fart. All right, and then over here, I'm going to ignore this radical for now. We're going to come back to that. But over here, I have x minus 5 cannot equal 0. And so I know for that rational expression that the excluded value there is that x cannot be 5. Now I need to look at that radical that I have. So I know that typically what's underneath a radical has to be greater than or equal to 0, typically. So I'm going to say x plus 1 is greater than or equal to 0. But in this case, that radical expression happens on the bottom of a fraction, and I know that on the bottom of fractions you cannot equal 0. So this equal 0 part, I got to get rid of. I can't have that. Okay? And then I'll go ahead and solve. So I'm going to minus the 1 over, and I know that x is greater than negative 1. So I have 3 things happening. I cannot have 0, I cannot have 5, and I have to be bigger than negative 1. So anytime you get to a problem like this, if there's multiple things happening and it's going to be difficult for you to write the domain, you are always able to draw a number line, and that can help you kind of like get your thoughts together on what you need to have. So we cannot equal 0, we cannot equal 5, I cannot equal negative 1, but I can be bigger than negative 1. So let's do this. Okay. So from anything bigger than negative 1. So from negative 1 to 0 is okay. Skip 0. From 0 to 5 is okay. Skip 5. And then anything bigger than 5 is okay. So that means that our domain is going to be from negative 1 to 0, from 0 to 5, and from 5 to infinity.